let's continue on now with logical operators. We have three logical operators, the logical and, or, and not. So the logical expressions are always evaluated from left to right, similar to relational operators. Right. The exclamation mark is the logical not. It inverts or complements, so not true is false, not false is true. Logical and, we'll see that the result of that is we'll have at least two inputs. When we have multiple inputs, all inputs must be true in order for the output to be true. And with a logical or, when we have multiple inputs, just one of the inputs must be true in order for the output to be true. So not has the same level of precedence as plus and minus. It has a very high level of precedence, meaning that the inversion or the negation will happen before the and operators and the or operators. They have a lower precedence than even the relational and the equality operators. All right, so we'll take a look at how these examples work. And first, go ahead and take a look at the truth table for the logical and. In this case, we have two inputs, x and y. Here's the output, x ANDed with y. Once again, the double ampersand is the and relationship. You can see here, this input is false. So we said when any of the inputs are false, the output is false. So false ANDed with false is false. False ANDed with true is false. True ANDed with false is false. The only time our output is true is when all of the inputs are true. So true ANDed with true is true. Okay, similarly, if we have a complex expression such as A less than B ANDed with B less than C, one of the best things you can do when you write code is to put parentheses around there to indicate the order of operations, right? Remember, parentheses force precedence. It just makes it clear to the reader what's happening in case they don't remember the precedence levels. In this case, the expression A less than B will be evaluated and then compared to B greater than C, and they both have to be true. We're saying the whole expression is true only if A is less than B and B is greater than C. Let's look at then the logical or. For the logical or to be false, all of the inputs to the or must be false. So the logical or symbol, right? Two vertical bars. Right, you have vertical bars on your keyboard, so we have two of these vertical pipes. So false ORed with false is false. But if any of the inputs are true, the whole expression will be true. So false ORed with true is true. True ORed with false is true. True ORed with true is true. So we see here, we had a true input. Here both inputs were true. The output is true. So you only need one or the other to be true. So and down here, same expression, but now with the or operator. This expression will be true if A is less than B or if B is greater than C. Right? When both are true, the whole thing's true. Okay. Logical not, once again, then we use the exclamation part. It negates it. Not 0 is 1, not 1 is 0. Now, we have to remember in C, we have arithmetic expressions. And what happens if we were to invert something other than a 1 or a 0? What you need to know about C is C always treats a 0 as false. False is 0, always. But anything that is a non-zero value. So logical negation of any C expression that evaluates to a non-zero value produces a result of 0. So not negative 54. C actually thinks of this as being true. So not true is false, evaluates to 0. Well, this evaluates to 3. It's a non-zero number. So this is saying not true. That evaluates to false. Now let's look at this expression. Remember, this is doing integer math, basically, right? Because this is an integer data type. This is an integer data type. Integer division happens first. Well, remember, with integer division, we only return the quotient. So the result of this is 0. 1 divided by 10 gives us a quotient of 0. So remember that 0 is false. Not 0 then evaluates to true or 1. Right? Well, I've given you then some example code in example 3 to see the output. of these relationships. Let me just bring up code blocks here. Here's example 3. And as you see right here, we're going to go through and we're going to see what the value of this expression, not 1, is. So the value of not 1 should be 0. It will be substituted into this placeholder right here in the printf. Right? We'll go through, we'll see what the value of this negation is, and then importantly, we'll see what the value of ANDing zeros and ones together is, what the value of ORing zeros and ones together is. We'll see that these match the truth table. Let's just go ahead, and I'm going to do a build and run here with example 3, and you can see not 1 turns out to be 0, not 0 turns out to be 1. So here, let's see, 0 and it was 0. So 0 and it was 0, that results in a 0. 0 and it was 1 results in a 0. Like we said, the only time the output of an AND relationship is true is when all of the inputs are 1. We get a 1 here. And then we have the results of the OR down here. So this section then shows you what the results of all these OR operations are. So 0 ORed with 0, 0 gives us a 0. Remember, all of the inputs to an OR relationship must be false in order to get out this false. If any one of them is true, the output will be true. So 0 ORed with 1 is 1, and so on. Right. So that gives you an example then of how these relationships work and the numerical results that we see with them. Let's just minimize that. And same way, if you're not running the program output is shown here on this slide for you. And as I just mentioned in the previous one, and I want to reiterate, that logical operators are non-zero operands. So anytime we have a non-zero operand, C will consider that to be true. Okay. So example 4 is a problem then where I'm showing you that if you negate 987, the result of that, well, this is going to be considered true. Not true is false. False evaluates to 0. Negative numbers are considered to be true. This will be false because it's truly 0. So if you go ahead and run example 4, if you run that code you were given, in this case, then we'd see, once again, we logically negate 987. Well, that's not true, that's false. This is not true, false. Not false is true, we get the 1. And I did the same thing here with the AND operators. So both inputs false, output's false. One input false, the other one true. Remember, output is false. One input true, the other one false. Output's false. But now it considers this input true, so our output is true. Similarly, for the OR gate, for that expression, that OR logical relation, when all of the inputs are false, the output's false. But when any one of these inputs is true, the output is true. So you can see here, this number is considered to be true. So C considers non-zero values to be true. 0 is false, always. Which leads us to short circuit evaluation. And short circuit evaluation has to do whether your logical operation fully completes all the comparisons in there. Right. Remember then that the leftmost operand is evaluated first. As soon as the value of the entire expression can be determined, the rest of the expression is not evaluated. And that's what we call short circuit evaluation, because as soon as we can know enough to know whether the whole expression is true or false, we don't have to complete the rest of this operation. So we short circuit this, and we're able to determine the final result just based on part of the comparison. Now remember, with a logical OR, we know that when any of the inputs are true, the entire expression is true. So as soon as we could determine that one of the inputs is true, we don't need to evaluate the other. I'm sorry about that. Let's come back to this slide. All right, so let's look down here. Here is an OR relationship, and I'm asking you, under what conditions will this statement be false? Well, we want to remember everything's compared from left to right. So it will evaluate this expression first, right? This comparison is evaluated first because of the parentheses to force order. Without the parentheses, it would be because the less than operator has a higher level of precedence than the OR operator. Remember, putting parentheses makes this easier to read. So if we take a look at this, we know that if I less than j turns out to be true, we don't even need to evaluate this side, because we know as long as one of the inputs to an OR gate is true, the whole expression will be true. And when this evaluates to true, we can call this short circuit evaluation, because we never come over and evaluate this expression on the right-hand side. Similarly, if we were working with an AND gate, we know that if any one of the inputs to an AND gate are false, the whole expression will be false. When I less than j is false, we do not need to evaluate the right-hand side to know that the whole expression will be false. It does not matter what k is. Let's go back then and take a look at our idea of under what conditions will I less than j ORed with not k be false. I less than j would have to be false, wouldn't it? Let's just actually go ahead and write this down. We bring up a blank file here. Okay, I'm just going to make a new blank text file that I can type in. I think I am. I need to learn the shortcuts for these. New file. I'm not going to write a C program. I'm just going to type. So our question was, under what conditions will this expression be false? We said I less than j ORed with not k, right? So how do we go about solving something like this? Well, we know that all inputs to the logical OR must be false in order for the output to be false, right? The whole relationship. All right. So we know then we have to say something like false ORed with false in order to achieve a result of false. Meaning I less than j and not k must both be false, right? All right. So I less than j is true for any, you could say any numbers, right? Any numbers where I is less than j, right? Basically, we're just reiterating that expression. As long as that holds, then this comparison is true, isn't it? And we want that to be false. So when will this be false? Well, I less than j is false for any numbers where j is greater than or equal to I. So there's our one condition. That has to be true. And then we said not k must be false, right? So not k is false for any value where k is not equal to 0, right? Because not true is false, so k can't be equal to 0. So in other words, j must be greater than I and k is not equal to 0. So we can say the expression, I'm just going to copy paste. Hang on a second. Is false when j is greater than or equal to I and k not equal to 0. Right. So the strategy we took for this, under what conditions will this expression be false? We rewrote the expression, we looked at this and we said, well, this is a logical OR. We know for this entire result to be false, all of the inputs must be false. Right? We said we had to OR false with false in order to get a result out of false. So here's one of the inputs, I less than j. We said, well, what do we have to do to make I less than j be false? Well, j must be greater than or equal to I. And then what do we need to do to make not k false? Well, we know that for any value not equal to 0, right? Because C programming considers any non-zero value to be true, not true is false, we have to say that k is not equal to 0 then. And then that makes that whole expression false. Right. So let's go back to this. Right, so this is your turn now to answer this. Under what conditions will this statement be true? I less than j and with not k. We'll follow a similar pattern. What do you know about the and relationship? You know that all of the expressions must be true in order for the output to be true. So under what conditions will I less than j be true? And under what conditions will not k be true? Determine that and you have your answer. Okay, now back to short circuit evaluation. We're going to take a look then at some sample problems. So we have example 5 and an example 4, or we're going to use the same relationship. So we're going to do some comparisons of I, j, and k, and then we're going to use some comparisons using the post increment and the pre-increment operator to see the difference between what operations actually are evaluated and to see examples of short circuit evaluation. Right, we'll have these values for I, j, and k. So let's go ahead and bring up those programs. So here I'm giving you the output of these programs, but let's just step through the actual code. All right. So I'm going to remove this from my project. Actually, it's not part of the project, so I'm okay. Remove that file, remove this file. So removing all files from our project, let's go to example 5 and here, and let's add this to the project, right click, add file to project, make sure it's in the debug release. All right, let's step through this program. So I've set I equal to 0, j equal to 1, k equal to 1. Let's use the debugger. We're going to step through the program. We're going to show what the values of I, j, and k are before we compare. And then we're going to do a comparison of I and with j and with k. Let's take a look at what we think is going to happen. We've got I is 0. We're going to have 0. J is 1. So we're going to have 0 and with 1 and with k. Let me actually just add this here and some comments. Right? I and with j and with k is 0 and with 1 and with 1. And this evaluates as 0 and with 1. And then that whole expression and with 1. And let's look at this. As soon as 0 0 and with 1 is evaluated as false, we know the result of the logical AND is false. And we do not, or the program does not evaluate these 0 and with K. Right? This is short circuit evaluation. All right. And we'll see then that after the comparison, the values of I, J, and K do not change. Let me go ahead and do a run to cursor here. We should rebuild. Okay, so in memory, we can see that I, J, and K are 0, 1, and 1. Here's our output then of the first comparison. Before the comparison, here's the values of I, J, and K. Here's the result of I, J, and K. The result is 0, it's false. And then you can see after comparison, the values of I, J, and K have not changed. So this expression, I ANDed with J ANDed with K, did evaluate to 0. Let's go ahead and see what's going to happen there here in part 2. So once again, we're printing out the values of I, J, and K before the comparison. And now we're going to talk about the actual comparison and the order of operations. Here's what we're going to do. We're going to compare plus plus I ANDed with J ANDed with plus plus K. Let's just go ahead and bring up the value, well, this is I, J, and K. Here, we can right here. Notice I is 0, J is 1, K is 1. Let's look at this expression here, plus plus I ANDed with J ANDed with plus plus K. Well, this leftmost expression will be evaluated first, comparing the results of plus plus I with J. Now, remember, this is on the left, so this is what we call the pre-increment operator, meaning we're going to add 1 to the value of I before we return what's in I's memory. So plus plus I here will cause I to be incremented by 1. So I is 0 right now in memory, but it will increment I to 1. It will return a value of 1. So then we will be saying 1 ANDed with 1, because we have a 1 stored in J. 1 ANDed with 1. We know that that result will be true. Because we don't know the full value of the expression yet, we know that one of the inputs to the AND is true. In order for the AND output to be true, they must all be true. Then we'll have to go over and perform the plus plus K, which in that case, we'll add 1 to K. K will become 2, right? 1 ANDed with 2 will both be true ANDed with true, and the whole result of this expression will be a 1, or true. So these comments walk you through this order of operations. This is what I just said. That the expression plus plus I is evaluated. Pre-increment adds 1 to I and then returns the incremented value of I. So plus plus I, that result of that expression will evaluate as a 1. J will evaluate as a 1. So we'll AND 1 and 1 together, resulting in the value of 1. Because that result is a 1, we can't fully determine the output of the AND relationship. We have to know that the entire expression is true only if all of the inputs are true. So we have to evaluate the plus plus K. That will evaluate to true. We'll compare 1 ANDed with 2, which will be true. But here's the order of operations. I'm trying to show you the order of operations here with the parentheses. Let's just go ahead and do a run to cursor to this point. You can see that we've got 1 in I, that value changed and K changed. So the debugger is showing you in red what variable values just changed. Here we can see the results of our output. The results of this comparison is a 1, it's true. After the comparison, there's the values of I, J, and K. Right. Now, I want to set I back to 0 here and K back to 1 because I want to perform the same comparison that we just did in this, but I want to change the pre-increment to post and show you how we get different results. We're actually going to have short circuit evaluation. So let's just go ahead and we're going to do a run to cursor so we can change those values. So run to cursor. Notice I is now 1 or 0 and K is back to 1. So we have our same relationship we started with. Here's what we're going to compare. We're going to compare I++ and it with J and it with ++ K. We're going to evaluate this. So remember then with post increment, the expression I++ is evaluated first. Right? It has a higher level of precedence than this comparison, that the post increment is going to return the value stored in I. So the post increment first will return the value 0 stored in I. Then it will add 1 to I. So we're going to then evaluate, right? This will be a 0, this I++, 0 ended with 1. That will be false. So I tell you right here, this will be false. The rest of this comparison out here, the AND ++ K, will not be performed because we know that the whole expression will be false. Short circuit evaluation says we don't have to do this. Right? So since this is not performed, we won't see the value of K change. Well, let's just go ahead and run that. Run the cursor. Right? Notice I changed to 1 because we actually return the value of 0, but then we add 1 to it. So I changed, but notice K never changed. So this operation was never performed. We see the result of this comparison is 0 for false because this returned to 0. Short circuit evaluation. What does this mean? Right, in terms of the code that you will write? I'm going to stop the debugger here. We tend not to write expressions like this. We tend to use these for learning tools to make sure that you can understand the order of operations. But as a coder, you don't want to write something like this if you need K to be incremented when going through this comparison operation. We tend to avoid writing code in that way. Like I said, we use these for exercises to help you understand what C is doing. But I would recommend not writing code in this way in your programs because you will often have unexpected results when this turns out to be false, especially when you want 1 to be added to K, whether this is true or false. So you have to be careful when you use these. All right, let's just go back then to our slideshow. So there's an example of the AND output that we just saw. Similarly, we can run the same example with an OR statement. Right? We're going to have the same values of I, J, and K. Right? We're going to see that when we have to OR everything together in this case. So an I0, so 0 ORed with 1, J is 1, will be true. Sorry, that will be true. We know as soon as this is true, we don't need to OR the K in with it. The whole expression will be 1. There was nothing in here to change the values of I, J, and K, so we can see that the output is still the same. But we want to remember that short circuit evaluation took place here simply because J was a 1. We knew that the whole expression will be true at this point. This code will never be executed. One way to see that is to literally use your debugger and step through these comparisons line by line, step by step. Here, we're going to compare, just as we did in the prior example, using the pre-increment operator, but now we're using ORs. Well, here's I is equal to 0. Remember, pre-increment says add 1 to I first. I becomes 1. This expression evaluates to 1. We're going to say 1 ORed with 1. We know this is true. We know the whole expression will be true. Short circuit evaluation. This operation never is performed. So if I start off with I equals 0, J equals 1, and K equals 0, you can see that when we get done, I has been incremented to 1, J is not changed. Once again, K is not changed because this operation was never performed. And lastly then, here's the same thing with the post increment on I. So we have I equal to J, I equal to 0, J equal to 0, K equal to 1 in this example. So I plus plus. This expression evaluates to 0. Then it does change what's in I's memory. Remember, think of this as returning the value of 0 for I and then adding 1 to I. So we can see that the output after this is changed, I is 1. But we're going to OR 0 with 0. 0 ORed with 0 is false. we still need to perform the rest of this evaluation because we do not know yet with the OR expression whether this result will be true or false. Here, K is 1, so we go ahead and perform this. Well, this evaluates to true, right? Because we add 1 to K, this returns true, so 0 ORed with 2 is true, so we get a value of 1 for that expression, true. And we see that K's memory was changed as well to 2. All right, so go ahead, practice those, change the numbers around a little bit if you want to see how pre and post increment works and to see examples of short circuit evaluation. All right. In our next video, we'll go ahead and start learning about the if statements.